Welcome to the Deep Dive. Today, we're immersing ourselves in a set of sources that they might sound like basic chemistry, but honestly, they form the absolute bedrock of industrial safety.
They really do. We're talking about the science of combustion, fire, and explosions.
And our mission for you today is pretty clear. We're going to decode the precise, the underlying mechanisms by which materials ignite.
And master the critical vocabulary you need to really assess and mitigate that hazard.
Okay, so let's unpack this. We have to start with the foundational knowledge. I mean, if you've ever had any safety training, you know the absolute minimum for fire.
The fire triangle.
The fire triangle. You need three things: fuel, oxygen, or maybe more accurately, an oxidizer.
Oh, that's a key distinction.
And an ignition source, which is just
Yeah.
heat. Take any one of those three away, and, well, the fire can't exist.
And that simple model is an excellent starting point, but it really only explains how a fire starts. It doesn't tell you how a fire sustains itself, which, is where the real danger lies.
Yeah.
To truly understand fire, we have to move beyond the triangle.
To the fire tetrahedron.
Exactly.
And this is where it gets really interesting, where the chemistry just takes over. That fourth component you add, the one that creates that four-sided figure.
Is the chemical chain reaction.
The chemical chain reaction.
Precisely. Fire is, at its heart, a rapid, self-sustaining gas phase oxidation process. It produces heat and light. Once there's enough heat to continuously vaporize the fuel, that chemical chain reaction it becomes self-perpetuating.
So the fire's feeding itself at that point.
It's feeding itself. The reaction produces enough heat to keep the whole process going, which means the fire no longer needs that initial external ignition source.
And understanding that is key to putting fires out, right? You have to break that loop.
You have to break that chemical loop. It's not just about cooling the fuel. Sometimes it's about using agents that chemically interfere with the reaction itself.
Okay, so when we're dealing with liquids, especially in, say, an industrial setting, the difference between a near miss and a full-blown catastrophe can come down to just a few degrees.
Absolutely. Which is why we need really precise terminology to assess the risk. We have to distinguish between a brief flash and a sustained burn.
And the two terms that sound so similar but are critically different are flash point and fire point. What's the scientific line between them?
Well, the line is really the threshold of sustained danger. The flash point, or FP, is the lowest temperature of a liquid where it gives off enough flammable vapor to ignite for just a moment.
So you get a flash, a little burst of flame, but then it just goes out.
It goes out, and that's the crucial part. The combustion does not continue at the flash point. There just isn't enough vapor being produced to feed that self-sustaining chemical chain reaction we just mentioned.
Okay, so what about the fire point?
The fire point is usually about 10 degrees Celsius higher. At that temperature, the liquid is generating vapor continuously and fast enough to sustain the chain reaction.
So that's when you get continuing burning.
That's when you have a real propagating fire on your hands. That small temperature gap is the boundary between, an alarming flash and a fire that needs serious intervention.
That distinction is incredibly clear. And the sources give this perfect real-world example. Petrol versus diesel. Petrol has an incredibly low flash point.
It's extraordinarily low, something like minus 40 degrees Celsius.
Wow.
And that extreme volatility is what makes it so dangerous. At pretty much any normal temperature you can think of, petrol is constantly producing flammable vapor.
Meaning the air around it is probably already a fire risk.
It's likely within the flammable range. Any tiny spark, even static electricity, will find that vapor and ignite it. Now you compare that to diesel,
Which has a much higher flash point.
much higher, often above plus 40 degrees Celsius. So unless you really heat diesel up, it's not posing that same immediate threat because it's just not evaporating enough.
And that's why handling diesel in bulk is inherently safer.
Exactly. At room temperature, there isn't enough vapor for a passing spark to ignite. You see this reflected in things like insurance premiums for, say, marine engines. The risk profile is just worlds apart.
Okay, speaking of temperature, there's another concept we have to cover. One that bypasses the need for a spark entirely.
Spontaneous ignition.
Spontaneous ignition. This brings us to the auto-ignition temperature, or AIT.
The AIT is the lowest temperature where a substance will just ignite on its own. With absolutely no external ignition source, you just heat the material up and boom, at that specific temperature, there's enough energy to kick off the chain reaction all by itself.
And this connects back to diesel in a really surprising way, doesn't it?
It really does, because even though it's less volatile than petrol, diesel's AIT is actually lower.
Which is how a diesel engine works.
It's the entire principle. You don't need a spark plug. The piston just compresses the air and fuel mixture, which raises the temperature inside the cylinder so high that it passes the diesel's AIT.
You get spontaneous controlled ignition.
A purely thermal mechanism, no spark needed.
So we've covered the temperature part of ignition, but you can have the perfect temperature, you can have enough fuel, and still, nothing happens if the mix with oxygen isn't right.
And this might be the most critical concept in all of preventative safety, the flammability limits.
Right.
We define the lower explosive limit, the LEL, as the minimum percentage of gas or vapor in the air that can actually sustain combustion. If the mixture is too lean,
Too much air, not enough fuel.
it just won't burn.
And on the other end, you have the upper explosive limit, or UEL.
Where the mixture is too rich. Too much fuel vapor for the amount of oxygen available, so again, it can't burn efficiently. The space between the LEL and UEL is what we call the flammable range.
And the main safety strategy is just to stay out of that range.
Always. You manage a process to keep the atmosphere well below the LEL. You don't want to just rely on removing ignition sources. You want to make sure the atmosphere itself can't catch fire.
The sources also point out how much the oxygen level itself affects this range. If you introduce pure oxygen, for instance.
It vastly widens the flammable limits. It makes things incredibly easy to ignite.
But you can use that knowledge in reverse, too.
You can. If we dilute the air with an inert gas, something like nitrogen or carbon dioxide, a process called inerting, we can narrow those limits.
So you squeeze them together.
You squeeze them together until they converge. If you get the oxygen concentration down below about 8 to 10%, combustion just becomes impossible. You've broken the chain by starving the oxidizer.
Okay, that idea of controlling the reaction speed transitions us perfectly into the ultimate danger zone. Explosions. An explosion is basically a sudden violent release of energy causing a pressure blast wave. But when it's driven by combustion, we classify it by speed.
Deflagration versus detonation.
Most of what we think of as normal burning, like a bonfire, that's a deflagration. The combustion moves at a subsonic speed, the pressure builds up, but relatively slowly.
Detonation, on the other hand, is it's a completely different class of violence.
Supersonic.
It's supersonic. And what's so fascinating is the positive feedback loop. The energy from the reaction creates a physical shock wave. That shock wave then compresses and heats the unreacted fuel ahead of it, making it react instantly.
Which creates an even stronger shock wave.
It's an exponential self-accelerating process.
And while detonation sounds like the absolute worst-case scenario, the sources show us that even a high-speed deflagration can be catastrophic.
Oh, absolutely. Especially with a massive escaped vapor cloud. We call these vapor cloud explosions, or VCEs. The Buncefield disaster in the UK back in 2005.
I remember that.
That was technically a deflagration of a huge petrol vapor cloud in the open air, and yet the blast wave was so strong it was heard hundreds of miles away. It shows that sometimes volume is more important than raw speed.
So how do we categorize these VCEs?
There are three main types. First, the confined vapor cloud explosion, or CVCE. This is when ignition happens inside a closed space, a building, a tank.
So the walls trap the pressure.
They trap everything. The pressure builds dramatically, maybe to 8 bars or more, before the structure just fails completely.
Like the ICL Plastics disaster in Glasgow in 2004. A gas leak in a basement.
A classic and tragic example. Then you have the unconfined vapor cloud explosion, a UVCE. This is more like Flixborough in 1974. A huge release of flammable gas into the open air gets ignited before it can disperse.
The damage is more widespread, but the pressure isn't quite as intense.
Generally, yes. But the third type is arguably the most dramatic and certainly the most feared.
The boiling liquid expanding vapor explosion. The BLEV.
The BAE, it's a very specific sequence of events. You need a pressurized vessel, usually with a liquid like LPG inside, and an external fire heating it.
Okay, so the fire heats the tank.
Right. And at first, the liquid inside absorbs that heat like a heat sink, and the pressure relief valve lets off steam, so to speak.
But the liquid level is dropping as it boils off.
Exactly. And as that level falls, the metal shell above the liquid line is exposed to the intense fire without any liquid inside to cool it.
So the metal gets superheated and loses its strength.
It weakens very, very quickly until it fails catastrophically. And at that exact moment of failure, all the remaining superheated liquid inside is instantly released from high pressure to, normal atmospheric pressure.
Which causes it to flash into vapor.
It does more than that. It violently flash vaporizes and atomizes. It shatters into this immense cloud of microscopic liquid droplets.
And that atomized cloud is the perfect fuel.
It's the perfect fuel for an instantaneous, massive fireball. The surface area is just enormous. So you get this combination of a huge fire radiating incredible heat, plus an intense blast wave from the sudden expansion. Vessel fragments can be thrown thousands of meters. It's that process of atomization that turns a tank rupture into such a destructive event.
We've covered gases and liquids, but so many common solids can be explosive too. Coal dust, grain dust.
Sugar, flour, plastics, metals, yeah.
This brings us to a new model, the dust pentagon.
Right. So a normal fire needs the 3 elements of the triangle, but a combustible dust explosion needs 5.
Okay.
You need your fuel, which is the dust. You need oxygen and an ignition source. But you also need 2 more things: confinement of the area and dispersion of the dust into a cloud. If it's just lying in a pile, it'll burn, but it won't explode.
It has to be suspended in the air.
It has to be suspended. And just like atomization in liquids, the key mechanism for solids is particle size.
It's all about surface area.
All about surface area. You can't light a big log with one match. But if you shave that log into fine dust, the surface area increases exponentially. Finer dusts burn almost instantly.
And how dense does that dust cloud need to be? Is it a lot?
Not at all. The lower explosive limit for dust is usually around 25 to 50 grams per cubic meter. Basically, if you're in a cloud of dust that's so thick you can't see for more than a meter or so, you are likely in an explosive concentration.
Wow. And that leads to this huge risk in these facilities, the difference between a primary and a secondary explosion.
And this is often the killer. It's a consequence of poor housekeeping. A primary explosion might happen inside a piece of equipment, like a silo or a mill, where dust is already suspended. It's localized.
But the blast wave from that initial explosion isn't.
No, that pressure wave travels out and disturbs all the dust that's been allowed to settle on floors, on beams, on equipment.
And it kicks it all up into the air.
Kicks it all up into a brand new, much larger explosive cloud. And the sources note that a layer of dust just 1 millimeter deep can create a 5-meter deep explosible cloud when it's disturbed.
A single millimeter.
The single millimeter. That new massive cloud is then ignited by the primary fire, and you get a devastating secondary explosion that can destroy an entire facility.
So managing that tiny layer of dust is literally a life or death measure.
It absolutely is.
So we've defined all these mechanisms. Let's pivot to the goal: control and prevention. How do industries turn all this physics and chemistry into actual safety protocols?
Well, they focus on managing the components we've talked about, the tetrahedron and the pentagon. And the sources give a really useful mnemonic for the 5 main principles of control. It's vices.
Vices. That's ventilation, ignition, containment, exchange, and separation.
And each one ties directly back to the science. Take ignition. That's about controlling sources, making sure their energy is below the minimum ignition energy for that substance.
Or containment, which is just keeping the flammable stuff inside the pipes and vessels where it belongs, so you never cross that LEL.
Exactly. And ventilation is your backup. If a leak happens, you disperse it so quickly, it stays below the LFL.
The separation part, using barriers, that leads us right into the whole regulatory framework.
It does. It leads to hazardous area zoning, which you see in regulations like ATEX. The whole framework is about classifying areas based on the frequency and duration of an explosive atmosphere.
Right. For vapors, you have zone 0, which is the worst case. The explosive mix is there all the time.
Or frequently. Then zone 1 is where it might happen occasionally. And zone 2 is not likely, and if it happens, it's for a very short time.
And for dust, you have the same idea with zones 20, 21, and 22.
Same probability criteria. And the beauty of this is that the zone tells you exactly what kind of equipment you're allowed to use in there.
Which is why you can't just take a normal power drill into a zone 0 area.
Absolutely not. You need Category 1 equipment for zone 0 or 20. It offers the highest level of protection because failure there is just not an option. Category 3 equipment, on the other hand, is only good for the lowest risk Zone 2 areas.
And this protected equipment comes in specific types, like flame-proof enclosures.
Right, often marked with a D. They're built strong enough to contain an explosion inside them and cool the gases so nothing ignites the atmosphere outside.
Or even better, intrinsic safety.
Designated I. This is a smarter approach. The entire electrical circuit is designed so that under any condition, it simply can't produce enough energy, either a spark or heat, to ignite the atmosphere. It removes the ignition source from the equation entirely.
And beyond equipment, what are the last big mitigation methods for pressure?
Well, we mentioned inerting earlier, cutting off the oxygen. The other major one is explosion relief.
Vents and panels.
Yep. You can't build every vessel strong enough to withstand the worst-case explosion pressure. It's not economical. So instead, you design engineered weak points.
So they fail safely.
They fail safely. Bursting discs or panels that open at a set pressure well below the vessel's failure point. It vents the pressure and directs the blast, preventing that catastrophic rupture.
So we've gone on this whole journey from the simple fire triangle to the complex dynamics of a BLE and the very specific threat of the dust pentagon.
It really shows that understanding these mechanisms and all the vocabulary that comes with them is the true foundation for managing catastrophic risks.
And it's all about oxidation. But we've mostly talked about oxygen from the air. The sources point out another danger.
The internal oxygen supply. This is what's so fascinating. Certain materials, strong oxidizers like ammonium nitrate or hydrogen peroxide, have huge amounts of oxygen chemically locked into their own molecules.
So they don't even need air to fuel a fire.
They bring their own oxygen to the party. If they get involved in a fire, they release that internal oxygen, which just supercharges the combustion, making it hotter and faster. It can push a fire toward an explosion. Or worse, if you mix them with the wrong chemicals, they can react violently all on their own,
Generating their own heat and their own oxygen.
supplying two corners of the tetrahedron with no outside help.
So what does this all really mean for you, the listener? I think what we've learned is that prevention is all about controlling the fuel, the heat, and most critically, the oxygen.
And that leads us to our final provocative thought for you to think about. The amount of oxygen available doesn't just decide if something burns, but it also decides what deadly byproducts are created.
Doug?
Think about methane, natural gas. If it burns completely with plenty of oxygen, you get harmless carbon dioxide and water.
But if you limit that oxygen, say, in a room where a fire has already used up a lot of it,
The reaction becomes incomplete. And incomplete combustion doesn't just make carbon dioxide, it makes highly toxic carbon monoxide and pure carbon, which is soot.
so controlling oxygen is the key to preventing the fire in the first place.
Yeah.
And to minimizing how toxic that fire is if it does start.
Exactly. It shows how fundamental control over that one single unseen variable is to preventing disaster in its entirety.